Continuing from the previous video, I now want to write the copy and filter functions. The goal of the copy function is to produce a deep copy of the list that you provide. So here I am assigning the result of the copy function to this variable L2. The goal of this, though, is that obviously if I iterate over L1 and L2 after this, I want them to have the same elements. But I want to go further, which is that I want L1 and L2 to be completely separate lists. I don't want to end up in some weird situation like this, where L2 appears to equal L1 because they're secretly just the same chain of nodes. I want a deep copy. I want a completely separate list with all of the same elements. So what that means is I want to make a duplicate of every node of L1 and then chain them all together and produce L2, or return that from the copy function. The filter function is actually pretty similar. So the filter function is to construct a copy of the list with certain elements excluded, but all of the other elements included. So in this down here, which we'll uncomment in a few minutes, I'm creating a copy of L1 that contains every element except for the number 10. Any occurrence of the number 10 is excluded. So it will just contain 6 and 17. But first, we're going to write the copy function. Now, I've mentioned previously that there are lots of cases in life where you have the opportunity to take certain shortcuts. And I'm going to begin by talking about one of those here. So I'm going to call this the clever but slow way of completing this task, which is, okay, so I'm going to want to return a new list. So I'll start by doing this. I'll make the head of my new list, and I'll set that to be a null pointer. And then I will observe that, well, wait a minute, I know how to iterate over my list L1. And if I want to make a list L2 that contains all the same stuff as L1, I do have a function that adds elements to my list. I could just iterate over L1, there's the number 6, insert the number 6 at the end of L2. Okay, now L2 is this. Now look at number 10, insert the number 10 at the end of L2. I could just use the insert at end function to add elements one at a time to L2, and thereby produce a copy of L1. And that's completely valid. If on an exam you were given the insert at end function and you were told, without being restricted from using it, you were told copy the list, go right ahead and do that. So we'll start by trying that. Because shortcuts like that are useful, oh, actually, I should have mentioned one thing I did between videos. I thought about this. I realized, it's probably not very nice to try and sum up an empty list. We shouldn't assume that a list with 0 elements has a sum of 0. So in my sum list function, I threw an exception. If the list is empty, we can't compute the sum. Okay, but since that was on the screen, I figured I might as well show that off. So if I want to copy the list, I could do something like this. I could iterate over the list that I was given, one element at a time, and for each element that I encounter, I could just try to insert that element at the end of my new list. So insert at the end, here's the head of the new list. Insert the value node arrow element. And then I return my new head pointer, the head pointer I produced after creating a copy of my list. So we'll try that out. This warning, as I mentioned in the previous video, is harmless for now because we just haven't gotten around to that function yet. So we try this out. And the testing code in main does the following. So first it makes a copy of L1, which is 6, 10, 17, 10, 10, 10. And then it prints out both lists, but first adds an element to each one of them. Because if the lists are truly separate and I add an element to each one of them, I shouldn't see the element I add to L1 in L2. This is the same way we diagnosed that shallow copy problem last week. And I think this copy worked correctly because when I print out both lists, the element I added to L1 is in L1 but not L2. And the element I added to L2 is in L2 but not L1. That is a good sign that both lists are truly separate. Okay, so I wrote the copy function. But did I really write the copy function? So this shortcut is great. It's absolutely fine to use a shortcut like this. The issue is not the shortcut, it's this insert at end. Every time I add something at the end, the function has to start at the beginning of L2 and walk all the way along and find the end. We might consider that that's a little bit wasteful. If I keep calling insert at end on a list of size 1 million, as I keep adding elements, I keep having to start at the beginning of L2, walk all the way to the end, and then add an element. Couldn't I just build L2 as I walk along L1? And the answer is yes. Although I should add, as far as 116 is concerned, if you're ever given the opportunity to use this shortcut, just use it. Unless the assignment or exam says you can't, then just do it. Speed is only an issue if speed is an issue. Otherwise, write code that works. So this is a clever way. I think it saves us some work. It allows us to avoid worrying too much about the mechanics of the list. But suppose that we want the fast way. So this is faster, but more tedious. Okay, well, I'm still going to want to create a new list. Node PTR, new head, and then I set the new head pointer to be null PTR. All right. And then what do I do? Okay, well, I'm going to want to iterate along L1. But this is a bit of a tough one. So I need to be able to know what I'm attaching to the end of L2. I'm going to begin by attaching a copy of the element 6 as my head. And then after that, I'm going to attach a copy of the element 10 after the node containing the 6. At each step, as I work with L2, I need to keep track of the existing last node in L2. I thought a little bit about how to describe this. If you had to write this code, it would probably require a little bit of trial and error to work out the design. Because I'm making a video, I had to think a little bit ahead about how I would design it. I've decided to do the following. Basically, if I'm making a copy of an empty list, that's easy. So if L1 is empty, then I just return a null. I just return the new head as it is. That is, a copy of an empty list is an empty list. Okay, so if I get down to line 108, that means that my list is non-empty, which means it has at least one node. I think what I'm going to do is I'm going to create the first node of L2 separately. So I'm going to say my new head is going to be make shared of type node. And let's see, at the moment, when I make my first node of L2, I'm going to copy the head of L1 to be the first node of L2. I'm going to set that, at the moment, it's the only node of L2, so I'll set the next pointer to be null, and I will set the value to be whatever's in the head pointer, the first node of L1. Okay, at this time, so as of line 109, both L1 and L2 have at least one node. L1 already has at least one node because it was passed in. L2, I've just created one initial node for. Here is what I'm going to do. I'm going to walk along both lists, and I'm going to keep track of the node 1 before the place where I'm inserting. So when I insert the 10, I'm going to keep track of the node before that in L1 and the node before that in L2. The reason I have to keep track of the node before is in L2, I have to know where I'm attaching my new node. And I'm going to keep track of the node before in L1 just to keep things looking symmetric. So it'll look like this. Node PTR node equals, let's see, the head of L1. Node PTR, we'll call that old node. So it's a copy, it's the node we're copying from. And we'll make sure to use uniform initialization. And then node PTR new node equals, let's see, the head of L2, so new head. All right, so what I have now are two pointers. A node in my new list, the last node of my new list, and the next node I'm working on in my old list. What I'm going to do at each step is I'm going to keep walking along. As long as there's stuff left over in my old list, I'm going to keep walking along and add it to my new list. In other words, because the node that I'm standing on, old node, is a node I've already copied. Notice how I've already copied it to L2 here. What I'm going to do is keep walking as long as there's anything after old node. In other words, as long as old node has a next pointer that's not equal to null. So I say while old node arrow next is not equal to null. So I'm going to actually write an English interpretation of this. Interpretation. While there are more nodes after old node. So remember that old node is a node we've already copied, and we're working on copying the node that comes after it. Okay, so while that's happened, while old node arrow next is not equal to null, there is another node that I can copy. So what I want to do now is go to that node, that's old node arrow next, and then copy the node in, and then set up the pointer from new node to point to the node that I just created. So something like this. New node arrow next, so this node is going to point to a node that I'm now going to create, equals make shared of node. And the next pointer of this node, the node I'm just creating, is going to be null because it's now going to be the end of my list L2. And the element in the node is going to be old node arrow next, arrow element, which is pretty disgusting. And as I said, I've tried a few ways of writing this, and I feel that even though that looks disgusting, this is at least one that I can draw out in a way that might be convincing. The operative word there is might. So if I want the value that I'm copying, I use old node, and then arrow next, arrow element. I have to follow the pointer from old node, I follow the pointer from there to the next node, and then I get the element. And then I copy that into this new thing. Okay, so now new node, arrow next is going to be the element 10. Old node arrow next is the element 10, and I move both new node and old node along. So I'm now going to have old node positioned here and new node positioned there. So every step, new node is a pointer to the last node that I added to L2. Old node is a pointer to the last node I copied from in L1. Okay, so now I have to set things up for the next iteration of the list. And let's just try this out. Let's keep going. So, okay, so is old node arrow next equal to null? No. That means there is still stuff left to copy. Okay, so I set new node arrow next to be a node containing 17. That would be old node arrow next arrow element. Okay, and then I set old node to be this, and I set new node to be this. I move them along by 1. Hopefully you can see that there's a lot going on here, and if you tried to write this function from scratch, you may not end up with the same design, but you also might have to spend an hour or so trying to figure out what to do. And it's always tough looking at somebody else's design, because even if I name my variables or I talk about it or whatever, it's still difficult to sort of reverse engineer what I had to do in my head to get to this point. So I'm walking along, I'm staying one step behind the insertion point so that I always know where when I'm working on the node right before the insertion point, I can always set the next pointer of that node to the next node that I insert. When I'm done, when old node arrow next finally equals null, that'll be in a situation like this. Old node points to the very last node of L1. And I guess we'll fast forward what happened in L2 here a bit. So there's 10, there's 10, and then there's another 10. And then when I get to the end, new node will point to this. New node is always a pointer to the last node that I created in L2. Old node is a pointer to the last thing I copied from. In this case, old node arrow next is equal to null. That means that there is nothing after old node, and that means I'm done copying. Okay, so that means when I'm done, I can just return the head pointer to L2. So return new head. And we'll cross our fingers and see if the compiler likes it. Okay, so it gives us that warning on the filter function again, but it does otherwise seem to like it. We run it, and the copy succeeds. But oh boy, was that a mess. That was a mess, and also I was able to write it in one pass by a combination of luck and the fact that before I made the video, I made sure I knew what I was doing. If I had to write this going into it cold, it would probably take me quite a bit of trial and error. Even I can't necessarily write this insert function perfectly on the first time through. There are too many things flying around. So keep that in mind. And I think, though, that this will prove the point. When I write the copy function 2 videos from now, the recursive version, I hope you will look at it and say, wow, that is gorgeous compared to this enormous mess. If you had to write this on an exam, I think you'd be quite rightfully nervous about it. Okay, what's next? Let's try writing the filter function. So the filter function is very similar to the copy function. The difference is I only copy some of the nodes. There are some nodes that will not get copied because they contain some value I want to ignore. And so I guess I have to sort of redraw L1 here. So there's L1, there's the head pointer, and then it does 17, and then 10, and then 6, and then 3 more copies of the element 10. All right. Okay, so there's my list L1. I would now like to write the filter function. The goal of the filter function is it takes some element to avoid, and then it returns a new list. This is going to be called L3 in main, containing every element of the list you passed in except the thing you said to filter out. So in this case, ignore all of the occurrences of 10. So here I've got 17, and then I'm going to end up with 6. And it turns out that's going to be everything because every other element is equal to 10. So I want to write that. And just like with the copy function, there is a clever way and there is a tedious and I guess a little bit faster way. And in fact, you can actually use the copy function as the basis for the filter function. You just have to add some extra if statements. Okay, so what's the clever way? Well, I make the head of a new list, and then I just walk along my original list. I'm going to scroll strategically here. I just walk along my original list, and I look at every element, and I only insert those elements that meet my criteria, the elements whose value is not equal to this variable filter value. So it's very much like the quick version of the copy function, except that I want to filter out certain things. So I'll say if the element of the original list that I'm looking at, node arrow element, is not equal to filter value, then I want to keep it. So in that case, I will call insert at end. And that's great. Just like before, this is a wonderful trick. It really allows me to save a lot of work because I'm trusting functions I already wrote to take care of the heavy lifting for me. So here it would walk along and say, okay, is 17 equal to 10? The answer is no, so insert it. Is 10 equal to 10? Yes, skip it. Is 6 equal to 10? No, so insert it. Is 10 equal to 10? Yes. Is 10 equal to 10? Yes. Is 10 equal to 10? Yes. And so it skips all 3 of these. Okay, we'll just try running that. Keep it, and just so I can steel myself for what I now have to do, which is to write the tedious version of the same thing. Okay, there we go. Okay, so in this case, we've got, it prints out, oh, sorry. As of part D, L1 also contains the value 999. And so in this case, the copy contains 17,6,999. So it skips over all of the 10s. Okay, so how do we write the tedious version? Well, we can use this as the basis for it, but it's still going to be pretty ugly, and there are lots of moving parts. So the first thing is, what happens if the very first node is a node that I have to filter out? Oh, that's already a problem. I'm going to actually come back to that. I'm going to begin by adapting the rest of the machinery. So in this case, just like before, what I would like to do is I walk through both lists in lockstep. So I keep pointers to the equivalent node in each list, and then I copy things over. The difference is there will be some iterations where I don't add a node to my new list. And so I'm going to begin by doing that. So I'm going to begin by saying, okay, first I'm going to ask the question. Old node, arrow next, arrow element. That's the thing I'm copying at this step. Old node, arrow next, arrow element. If that is equal to my filter value, then I do not want to copy this node. I skip it. So I'll say just move old node along. I don't move new node along because I haven't changed anything about the list that I'm copying stuff into. Otherwise, it is a value that I do want to copy. So I'll just jam all this stuff into an else clause here. And we'll try running that. I guess in this case, in this case I should have to comment out this thing. So I have to comment out the clever way, even though I think in practice, in the absence of other restrictions, that is the best way to start. And then I'll try running it. And I want to talk a little bit more about it. So we can see it does work. And so you may need to rewind the video to remind yourself of the logic that I'm using with this old node and new node business. And the idea here is, again, that at every step, old node refers to the last place I copied from. So if I were to line it up with this diagram here, I just copied the element 6. That would be this is what old node points to. So I'll just write old. And new node is a pointer to the last element, the last node you created in your output list. And the idea is that way it's easy to make sure you know where you're attaching the nodes you create next. In cases where old node is, so if I'm working on a node that I'm supposed to filter out, I just want to skip over it and go on to the next one. I don't change new node because nothing has changed about my output list. That is the idea behind this if and else, although I agree that explanation may not do it for you. One more reason why this iterative formulation is pretty nasty. But we have another problem, which is there's also this really ugly special case, which is what happens, and I'm going to delete my diagram for this. When we copied lists, we began by creating the new head pointer by just being a copy of the first node. But what if the very first node of the list, of my input list, is one of the values I have to filter out? Oh, that's quite a headache. And so what I have to do here is I first have to find the very first node that I copy, because it may not be the first node of my input list. And so I think I'll try doing this. I will say first, we're going to iterate along and say, while old node is not equal to a null pointer, I'm just going to keep walking along and see if I can find the very first node that I have to copy. So if, well, actually, I guess I could use two conditions here. And old node arrow element is equal to filter value. So what I want to do here is I want to skip over all of the initial nodes of my input list that I'm going to be filtering out. So in that case, I just do old node equals old node arrow next. So I can sketch out what I mean there. So in this case, suppose I have a list where I'm filtering out the value 10. But suppose that the first few elements are all 10. Well, the very first thing I actually want to deal with, the first node I'm going to copy is this one. But if I started ahead, I'm going to copy a 10. So what I'm going to do is I'm going to start by pointing at the first element, and I'm just going to walk along until I find anything that I can copy. So I just keep walking. That's what this is doing. It has this check here because what if every element of L1 is equal to the value I want to filter? Well, then I'm in real trouble. And in that case, I can catch that down here. So I can say, well, if at the end of that loop, old node is equal to a null pointer, well, then we're out of luck, right? There was nothing to copy. And so I just return new head in its current state, which means that the output list is simply empty. Okay, so then I get down here, and I'm ready to add the very first element to my new list. So that would be this situation here, where the first non-filtered element isn't at the beginning of the list. So I've walked along to find the first non-filtered element, and now I create explicitly a copy of that. So it'll be old node arrow element. All right, and so now I have the very first node. So there's I guess conceptually my L3. I now have the very first node. This is my pointer old. I have the very first node of my list L3. And now on line 150, I set my pointer new node to point to the last node that I created. And notice that at this point, as of the end of line 150, old node and new node are set up the way that we remember from the copy function. Old node points to the last place you copied from. New node points to the last node you created. And so that means now I can jump right into this while loop that I already had. We'll run that, although I should add that the testing code, you might have to do your own testing of this case. The testing code doesn't actually contain the case where the first element is the number 10, is the filtered element. You may just have to take my word for it. What I will observe is this is a nightmare. I could not reasonably expect somebody to get this in one pass, or even given an hour worth of debugging. There are a lot of cases. It's hard to even know what all of the cases are. It is an absolute nightmare. And to be honest, writing this in a video, even though I already knew the solution, I was worried that I was going to forget the solution and not be able to get it. I might just fumble around, which I do in most of my videos, so I am sort of used to that by now. But this is really messy. And if you look at the trick we did in the clever version, you can see there is quite an asymmetry between the conceptual complexity of the task, so that's sort of close to this, and the complexity of the task if you write it raw, if you write it piece by piece, micromanaging everything. It is a mess. There are so many places that bugs can show up that you might not even know could exist, much less that are occurring. And that's one reason why knowing a different design pattern, for example, a recursive one, could be really helpful. And so in the next two videos, I'm going to go through all of these list functions again. I am going to do all of them entirely with recursion. And right off the bat, in the next video, we're going to see an example of a function that's even more of a nightmare than the filter function, something I wouldn't dare to try writing iteratively that will turn out to be a piece of cake with recursion.